Good. So this is our topic for the evening. Not very difficult. It's mathematics that may not be new to you if you once you went to a secondary school, you might have touched on this topic, right? Relations, functions, and we'll do a little bit of graphs, right? Go a little beyond what the course outline asks for. They did talk about graphs a little later on, right? But I'll do it right now because it's good for you to see how they're all related, right? So what is a relation, right? In mathematics, that's a nice definition you see here. A relation is basically a set of ordered pairs, right? And this is an example here. This is a pair, that's a pair, that's a pair, that's a pair. These are all pairs. But they use the word, okay, it's a set, so you see curly brackets here. But they said it, they are ordered. They are ordered. And the reason they say that is because there's some kind of order to these pairs. There's some kind of, and there's where I want to bring in this word. There's some kind of relationship between this number in the pair and this number. And tell me if you can spot it. Look at this number, look at this number, look at this number, look at this number, look at this one, look at this one. What's going on? What do you notice?
Two stars.
Good night, everyone. So,
The number goes up 2 times in the pair.
You can't put a word, word times. It doesn't go up 2 times.
what?
Times kind of tell you multiply. What do you do to the first one to get the second one?
You add 2.
Add. Very good. Very good. Right? So using the right word now. It's like you're adding 2. Right? Great. Yes. So there's that order to every pair. It's not all just 0, a negative number here, 1, a positive number here, and all mixed up. No, there's some order. There's a definite relationship, right, between the first number in the pair and the second number, right? And that's why we're saying it's a set of ordered pairs, right? So, yeah, great that you can pick out that relationship that you see there, right? Yeah, nice. So we're going to express this ordered set of ordered pairs in different ways in just a moment, right? But we want to, kind of clarify some things called, some terminology there, right? So we start with this word here, domain, right? So we say the domain of the ordered pair R, or the domain of the relation R is, notice, we are taking all the first numbers in each ordered pair. And we call that the domain. Now, when we go on, you're going to see that we can liken functions to like a machine, It's a mathematical machine. Right? Relations are like that. Relations and functions are like mathematical machines. And the input, right? We call the members of the input the domain. Right? So these force numbers there, 0, the 1, the 2, the 3, the 4, we'll call them the domain. Right? You can think of those as the input into the relation or the function, right? Input. Next, we have another group of numbers called the range. So the range of the relation R is the set 2, 3, 4, 5, 6. This is like the output of the function or the relation machine, you know? So it is the output, it's this. You put in 0, you get out 2. You put in 1, you get out 3. You put in 2, you get out 4. You put in 3, you get out 5. You put in 4, you get out 6. So the range is actually the output. What is going to come out of this machine, this mathematical machine that you have? Right? You getting that so far? Is it making sense?
So sorry, if it was like sets of 3,
Sets of 3 as it, oh, you want three numbers there?
yeah, if it was like sets of 3, would the range be 2 numbers?
No, hold it. Watch this. Remember, the definition of a relation is pairs. So you can't have 3 of them in here. You can't have 3. You can only have 2.
Okay.
Very definition says you're dealing with pairs. I'm happy that you're thinking out of the box and you wish the thing is a little more complicated. That's not bad. But relations involve just pairs. Right? Yeah. So here we are. We got our domain, we got our range. There is another relationship that you will want to, well, you'll hear about it as you study relations and functions. You will hear of something called a codomain, right? And what happens very often, the range is usually the same as the codomain, or it could be contained in, and that's what the symbol means. The range is a subset of the codomain, or you can say the range is contained in the codomain, right? So the two can be equal, or the range can either be a part of the codomain, right? And what the codomain basically is saying, the codomain is like a broader set from which the range is taken. So the codomain here could very well be like, okay, for this relation, the codomain could very well be this. So the codomain, and sometimes you see codomain, right? I need some more space there. All right, let me put codomain, right? I'll just put C. Is equals to, you can very well have 0, 1, 2, 3, 4, 5, 6, 7. Your codomain can be a little bigger than your range. It can also be the same as the range, right? Now, how are we to understand what we mean by the codomain, right? So sometimes a machine can do several things, right? It can do several things. But what comes out of this machine depends on what you put in, right? What comes out is what you put in. Like, okay, take your printer at work. I don't know, you all work, right? Your printer at work. Your printer can print black and white, right? It can print color. It can scan maybe, right? So it can do all these things. But depending on what you put in, you might not get out all the possibilities. So you might put in a black and white piece of paper, right? Black and white. And you can't get out a color copy out of it, right? The printer can't just give you a color copy, it will give you black and white. So while it can produce color copies, because your input is black and white, you will get out black and white. right? A copy that is black and white. So here you have a situation where the printer has a great capability. It can scan, right? It can make color copies. It can make black and white. But your input is such that you are not getting, you're not going to get all of the possible output, right? Sometimes simply because you didn't scan the document, you made a copy, right? Your printer can also have an electronic image that you can send somewhere. You don't necessarily have to print something. It can save that image and send it somewhere, right? You have printers like that would print and scan, right? I have one like that. So it doesn't always produce a copy, as in hard copy, like a paper. So the printer can do all these things. It can print black and white. It can print color. It can scan. It can produce an electronic copy of what you put in. However, because you put in a black and white image and you press print, right? Or copy, sorry, press copy. The thing gives you a black and white copy. It only gives you a subset of all the other possibilities. And that's a good illustration of what we mean by range and codomain. Codomain is all the possibilities that you can get out. But your range depends on what you put in. Your range is just a subset. Sometimes it's equal to the codomain. Sometimes it's just a subset. Do you follow that? Let me ask you a question. For your range, let me see if you're thinking now. For your range to be equal to the codomain, for you to get all right, we already got these. How could we have gotten 0 and 7? How could we have gotten 0 and 7? What should be in the domain? If we want 0 and 7. Let me see if you're thinking.
Or maybe -2 for the 0.
Great. This person who's answering is thinking, yeah, if the domain included -2, and what else? Right? So if we had -2 plus 2 would give you 0. And how would we have got 7? What we need to include here?
Positive, -7, sir.
We want to get 7 out. What we need to put in? What we need to put in?
Oh, wait, you want to get it out? Do you mean like remove it?
We want to get 7. Okay, you see this range here? We got 2, 3, 4, 5, 6, but we don't notice the codomain is 0, 1. How do we get 1? What do we need to put in to get 1? To get 0, we put in -2. To get 1,
-3.
no, -3 plus 2 will give you 1. What do you have to add to 2 to give you 1? When we add 2 to negative 2, you get 0. But what do you add to give you 1? To give you 1.
Or -3?
Negative 3.
-1, sir.
You're guessing, man. Negative 3 plus 2 will give you 1. Where you get it from?
Sir, -0 plus 1 will give you the 1.
Negative 0 and all people talking about. Oh my.
Or sir, it's -1.
Negative,
But-
negative 1. If you add 2 to it, that will give you this one, right? Yes. And 5, if you have 5 inside here, 5 and 2 will give you the 7. So now your range is going to go from 0, 1, 2, 3, 4, 5, 6, and then 7. So in this case, your range now equals your codomain. You see? So while the codomain is this bigger set, your range is just a subset of it. But you could make it that way if you increase what the the domain is, right? If you extend the domain. If we go from -2 right up to 5, well, we can cover the whole codomain, right? Think about it. Think about it. Part of it also is going to be in the video, and when you get to watch it back, you're going to be able to see what I'm saying, right? So we go to, all right. So how do we represent relations? How do we represent the relation? Well, we just did this one, right? We use set notation. But then we can also use a little bit of algebra to represent it. And we can say that X is such that X maps onto X plus 2. Right? We say X is such that X maps onto X plus 2. Right? And we said that. We said that, okay, we take this first number, we add on 2, and we get 2. Take this first number, we add on 2, we get this number, and so on, right? So we're saying the relation is like you're taking an input, and this is the output. This is the input, and this is the output. The input is X, the output is X plus 2. Do you follow that? So we can use either the set notation, or we can use some algebra. And we can even represent this using what we call the mapping or an arrow diagram, as you can see in this picture here, right? So all the members of the domain is that in that first loop, right? And the members of the range is in the second loop, right? Sometimes I've seen mappings where instead of the range here, they put the codomain, right? And the other members of the codomain can be put in here, right? And missing the ones that you want to include. That can happen to you. And you draw an arrow to, well, 0 maps to 2, 1 maps to 3, 2 maps to 4, and so on. And because you see that, you know, everybody has their pair, right? One arrow leaving here, going to one there. We call it a 1-to-1 relation. 1-to-1 relation. Go and go there. Good. So we can also represent this relation on a graph. On a graph. Later on, you will learn that the graph you're seeing here is what we call the Cartesian coordinate plane. Cartesian coordinate plane, right? Sometimes instead of this big word, they say the XY plane, XY plane. Sometimes they even say the XY coordinate plane too, right? XY coordinate plane. Here, you plot the values of X, right? And they call this the X-axis. And here, right, sometimes you hear they call this the Y-axis or the FX-axis. Well, we haven't reached it, right? We haven't reached it. So for now, we're going to say that this is the X plus 2 axis, right? Because we're only dealing with this relation, right? So notice 1 mapped on to, sorry, was it 0 to start with? 0 to 2. So you go with where 0 is. 0 is anywhere along this line. And 2 is anywhere along this line. And where the 2 intersect, that's the point 0, 2. Right? Then 1 and 3 was paired together. So anywhere along this line is 1. Anywhere along this line is 1 on the x-axis, right? And anywhere along this line is 3. And you notice the 2 intersect. So this point is the point 1, 3. Right? And the same reasoning. Anywhere along this line is x equal 2, right? Anywhere along this line is y equal 4, where the 2 meet up together. You call this point 2, 4, and so on, right? And so on. You follow that?
Yes, sir. Yes, sir.
Not difficult, not difficult. But it's good for you to know to read off a point on a graph and so, right? And how to plot a point. Very important. So we're taking another example. So we have a set of ordered pairs here. -2, 4, -1, 1, 0, 0, 1, 1, 2, 4. No? And if you look at it carefully, you can see like it's you're taking the first member of each pair and square it, and you get the second member. Do you notice that? -2 squared gives us 4. -1 squared gives us 1. 0 squared gives us 0. 1 squared gives us 1. 2 squared gives us 4. Do you notice that?
Yes, sir.
Yeah. How do we represent that algebraically? Let me say x is such that x maps onto x squared, right? X is such that x maps onto x squared. And let me give you a joke. There's a frog on my screen, and the frog, when it sees the cursor, thinks that it's a fly or mosquito, and it's jumping on it. Get out, and get away from me. They don't understand the technology. So how do we represent this with a mapping diagram or an arrow diagram and then a graph? Let's see. So this is what the mapping looks like, right? It's a little chaotic. Yeah. It was a little chaotic. So we start from -2. The square of -2 is 4. And then -1 is squared to get 1. 0 goes to 0. 1 goes to 1 again. And 2 goes to 4 again. So what we're seeing here, right, is a little more chaos. But you're seeing sometimes over here, okay, you still have one arrow leaving each member, just one. But over here, you have situations where, like the one here, 2 arrows coming to it. Before, you have 2 arrows coming to it. So we refer to that as what we call a many-to-one relation. A many-to-one relation. Right? Because what? In the case of -2 and 2, both go to 4. So it's 2 going to 1. Right? More than 1 going to 1. Many to 1. You see the reason why we give it that name? Now this is the graph. Right? This is the graph. So these are the x values. The x values are on the x-axis, right? Or the input. These are like the inputs. -1, -2, -1, 0, 1, 2, 0. So those are the inputs, and then the outputs now, let's see. -2 go up. That corresponds to 4, right? And the 2 of them meet there. So that point is -2, +4. Here, -1 is anywhere on this line. 1 on the y-axis, or the output axis is there. So the 2 coincide there. So this point is -1, 1, and so on, right? And when we join them up now, we got this nice curve, right? Later on, you'll find out that the name of this curve is a quadratic curve, right? And you'll see that many-to-one oftentimes, not always, but you have situations where it's a curve, and look what here. Each number here might have 2 inputs producing it, like what? -1 and 1 produces an output of 1, right? -2 and 2 produces an output of 4, right? So 2 inputs can produce the same output, right? And again, you can think of devices that are like that, right? you have a printer, and not always do you have to put a paper in order for it to print something. You can put in a flash drive with a digital image, and it still produces, it prints something for you, right? You can send a digital image from a computer to it. So you can have several inputs, different inputs, but it's producing one output, a copy of that page, right? A hard copy. Right? So yeah, these ideas are all borrowed from,
So,
yeah.
sir, it could be like when you print in one notes on two-sided of the page, but you're using one page. Is it that like in that way of example you're trying to say?
No, I don't think I'm trying to show you how a different input, two different input, right? You could use a real paper, you could put a paper in the printer and produce another paper, but it doesn't have to be a paper. You can very well use, as I said, a digital image from a computer or a flash drive. I don't know if you go to these printing places, you'd always take a paper. You could take a paper and the people put it in the printer and it prints. But sometimes they tell you, give me a flash drive. Give me the thing on the flash drive. You put it in the computer sends it to the printer, and you get an output. Same output that you get if you give them the paper. Right? So yeah, these ideas are borrowed from mathematics. Lagore used to make one thing to do one thing. The phone used to make phone calls, that's it. Camera used to do one thing, take pictures. Now they have this thing called your cell phone that, well, you should never, they need to get rid of that part where it says phone and just call it maybe cell or something. But it does everything. Well, the cell phone is an example of what we call a many to many. Many things go into it and many things come out. That's too complex for us. Yeah. So let's take a final one. This one is a little more complicated, right? It might be difficult for you to guess what's happening to the first element to give you the second one. It might be difficult, right? But let's see. It's basically X is such that X maps onto the positive and negative square root of X. Right? Look at it good. The square root of 0 is 0. The square root of 1 is both -1 and 1, right? So you see that here. 1, the square root is -1, as well as the square root of this one is +1, right? I think somebody was asking whether we can't have 3 in a pair. Well, a pair has to be 2, right? But this is the best we can do, where we describe, instead of putting 1, okay, confusing things, and put 1 and then 1 and -1, that'll be confusing. So we say no, 1 and -1, and then 1 and 1, right? We preserve the definition that we're dealing with pairs. Clear so far? So let's see what this looks like on a graph. Oh, sorry, on a mapping diagram. So here you're seeing some chaos. But if you observe here, this is very different from the rest. You're seeing 2 arrows sometimes leaving a member of the domain, right? Same thing here. 2 arrows leaving a member of this This one here, 4. Same thing with the 9. Right? So that's why they call it one to many, right? Because what? This one is going to more than one over here. Similarly with the 4, 2 arrows leaving it. So we say 1 going to many. So it's a one to many relation. Still with me? Are you still with me?
Yes, sir.
Yes, sir.
Yes, sir.
Don't get lost. How do we represent this? Let's see. We represent it on this graph, right? So the input again is on this horizontal axis, what we call the x-axis, input axis. Output, or the y-axis, is here. So 0 and 0, right? This is the point 0, 0. 0, 0 is that point here. Then anywhere here is 1 on the x-axis. But here is 1 on the output axis, and here is -1, right? So this point here is 1, 1. And down here is 1 -1, right? And then here, okay, anywhere here is 4. Down here is 2 on the output axis, and down here is -2. So this point here is 4, 2. This one is 4, -3. And so on. Follow so far?
Yes.
Taking long to erase. I don't want to spoil the PDF. I think if you don't erase this, it will be left with me. When I scroll down, I think it might. Think so. Damn it. So next we want to go to a new type of relationship. Not new, sorry, a related relationship, right? Which we call functions now. And this is what it says here. This is a technical definition of what a function is. It says that a relation can be classified as a function if certain conditions are met. What are these conditions? It says each element of the domain, for each element of the domain, there is one and only one element of the codomain. Right? Now, what I is saying is that if you were to, when you watch the mapping diagram, for example, right? And let's say you have, all right, 3 elements here. One arrow must leave and go across here, right? One arrow must go across here. You can have this arrow going there and all, but the main thing is that each element over here has to have an arrow leaving it. If you have an element there that no arrow is leaving it, no, you don't have a function, right? But if you have an arrow here that element here where 2 arrows are leaving, no, that's not a function, right? And to help you a little, all one-to-one function, all one-to-one relations and all many-to-one relations are functions. Right? Just to give you a little help in terms of the arrow diagrams. So if you see a one-to-one relation, yes, it's a function. Right? If there's a many-to-one relation, it's also a function. But remember, you can be fooled. You can have a one-to-one relationship, right? 1, 2, 3, 4, let's say 5, okay. And here's one arrow leaving there, okay. And one of them, nothing leaves it, right? Be careful. Be careful, right? You may not have a function if that happens, right? How do you recognize it from the graph? How do you recognize it from the graph? Well, all right, I'll skip this over. I want to go to a graph. All right. All right, all right. I'll have to let me use a piece. I don't want to get into this. Is for some higher maths. Let me stop here and I want to go over to a whiteboard, right? Let me share a whiteboard. So, how do you recognize it from a graph? So if you have a graph, okay, let me say it's a straight line graph because we dealt with a straight line. Then we had a graph looking like this. And then we had a graph looking like something like this, right? So if you were to draw, they call it the vertical line test. Vertical line test, right? To identify a function, right? So if you draw a vertical line, let me use a different color. If you draw a vertical line, vertical line, vertical line. If the line cuts the graph only once, well, these are functions. But if it cuts twice, these are not functions. Right? If you're given a graph, you want to know, well, does this graph represent a function? Do this test. Draw a vertical line. If it cuts the graph once, you have a function. If it cuts more than once, no, that's not a function. You agree? We're okay there? And now, when we know that a relation is a function, we no longer write it like this. X is such that X maps onto X plus 2 and so on. Right? We write Fx maps onto X plus 2. And later on, we'll drop this arrow now and say Fx is equal to X plus 2. Right? Sometimes we can read it this way. The function of X is such that Fx is equals to X plus 2. If you don't want to repeat the part about function of X, you can say, sorry, if you don't want to mention back Fx, you can say the function of X is equal to X plus 2. Right? Or you can say the function Fx is equal to X plus 2. All those are possibilities. So from now on, once we're dealing with a function, you will see a little F in front. Not F alone, they can use other letters. You can see GX, you can see HX, and so on, right? FX is very common. Good. So let's go into some function operations. So what are some things you can do with functions? Well, you could add functions, you can subtract functions, you can multiply functions, you can divide functions. Yeah, you can do all of that. And that's what is captured on this page. It looks a little complicated, right? You can add them, you can subtract them, you can multiply them, you can divide them. And you've been doing that, right? You can add two functions, like if you have, I think there are examples after this. Let me give you a minute to process. There's a whole lot of this particular slide, so give you some time. So this is the addition. This is the addition, that's the subtraction. This is the multiplication. This is the division. And later on, we'll come to talk about what we call forming a composite. That's different. We'll get to that in just a minute. So let's go up. This is a nice example here. So we're adding, we're subtracting, we're multiplying, right? I'm going to use the asterisk here to mean multiply, right? And then we're going to divide. So you have two functions. This is one, 2 plus 3x minus x squared. And another function, gx, equal 2x minus 1. So we add them, right? We add them. And remember, we were doing addition of algebraic expressions. You all remember we did that? Where you add like terms, right? Look, 2 minus this one gives you 1. 3x plus this 2x gives us 5x. And there are no other x squared terms, so we put back minus x squared in. You follow that? We add like term. Similarly with subtraction, we subtract like terms, right? So 2 minus 1, those two minuses will become a plus. So you get 2 plus 1, that's how we get 3. 3x minus 2x will give us x. And then there are no other minus, no other x term, right? X squared term. So we leave the minus x squared in, right? If you're having trouble figuring out this, let me show you what happens. You're going to remove the bracket. Remove the bracket. So you get, what should you get? You get 2 plus 3x minus x squared. This minus 1 by that will be minus 2x. This minus 1 by this minus 1 goes positive 1. So this 1 and this 2, that's how I got that 3. This 3x minus this 2x, that's how I got that. This is left at the end, so we put that back here, right? Clear? Multiplying is a little harder. 2 multiplied by this 2x gives you 4x. 2 multiplied, okay, I think what happened here. Let me see, let me tell you what happens here. Let's multiply this one. So 2 multiplied by this 2 gives you the 4x. 2 multiplied by this 3x gives you 6x squared. 2x multiplied by minus x squared gives you minus 2x squared. Then you multiply everything by -1. -1 by 2 gives you -2. -1 by 3x gives you -3x. -1 by -x squared gives you positive x squared. And now you simplify, right? So 4x minus this 3x gives us this x. 6x squared and this one more becomes a 7x. Minus 2x cubed, there are no other x cubed terms, so that remains the same. And there are no other constants, so that remains the same, right? It's kind of done in a jumble way because I did this for a more advanced class. So they would have understood it, you know. I'm sorry that I use it for you. But you're smart, take some time and analyze it, and you'll see when you simplify this, you will get that. And the division, there is no kind of simplification that we can do here, really. There is, but it's above you. It's above you. We'll get there later on. What we want to go next to is something called the composition of function or function composition, right? And basically what this is talking about is the same. We were referring to cell phones and printers and so earlier. Long ago, as I said, one instrument does one thing. Camera takes pictures and that's it. Right? A phone makes phone calls and that's it. A printer prints images and that's it. Now that's not the case. We have devices now that do multiple things. The cell phone being the prime one, right? Even your printers now at work is going to do scanning, it's going to print, right? All kinds of things it does, right? So yeah, that's basically you're taking a several functions and combining it into one device. Well, here we are going to make one function do what several functions would have done, right? So let's see how it's done, right? So let's take two functions. Fx is this one and gx is that one, right? And we are going to lower that first one, lower the first, the A part. Let us look at the composite of f and g, and then the composite of g and f. Notice we're using a little circle like in the middle there, right? Different textbooks might use different symbols, right? So the composite of f and g and the composite of g and f. In some textbooks, they actually have the composite of f and g as this. They actually have f gx and they have g fx. They don't write it like this. And that is the composite. That's different from this. This is the product, right? But this here is a composite, right? So how do you find the composite? Well, just like if you have a function, all right, let's say you have fx equal to this here. Now, if you want to find f1, what you do? You normally put 1 in here. So you have 2 plus 3 times 1 minus 1 squared, which is 2 plus 3 minus 1, which is 5 minus 1 is 4. So whatever is in here, you put in the place of x here. So we're going to do the same thing now, but we're not putting, watch here. So the composite of f and g is that you're putting the whole of gx, which is 2x minus 1, right? Look here. We're putting the whole of this in the place of x here and here. That's what we're doing, right? The 2 plus, it's supposed to be 3x, but we're taking 2x minus 1 now as x. It's supposed to be x squared, but we're putting 2x minus 1 in there. And then we are going to expand this out, right? So 2, we put back the 2. 3 times 2x gives you 6x. 3 times minus 1 gives you minus 3. And then we expand 2x minus 1 square. And remember we did that. It's like 2x minus 1 multiplied by 2x minus 1. Right? I remember doing this when we were doing factorization. 2x by 2x gives you 4x squared. 2x by minus 1 gives you minus 2x. Then this one, all right, let me write it. 2x by 2x squared. Sorry, 2x by 2x gives you 4x squared. 2x by minus 1 gives you minus 2x. Okay. Yeah. So let me go back this part about function composition because I don't know how much you got. Yeah. So as we said, you know, if we want to combine two functions, we perform what we call function composition. So in this example, you want to form a composite of G and F, right? F and G, and then G and F. Forget this one. This one means you multiply the two, right? So we're not going with this. That was done in the previous exercise. So we're going to do the composite of F and G and then the composite of G and F, right? So just like if you wanted to find out what is F1, what we would have done is we would put 1 in the place of x, right? So you have 2 plus 3 times 1 minus 1 squared, which is 2 plus 3 minus 1, which is 4. So now we're not putting a number 1. We're putting a whole function, as you see here. The composite of f and g is like you're putting the whole of g of x in the place of x in fx, right? We're putting the whole of gx, which is 2x minus 1. We're putting it in the place of x, right? You see these x's here, we're going to put it in a place here. And that's what we see happening here. And then we are going to simplify the bracket, right? Simplify the bracket. So 2 come back, 3 by everything in the bracket gives you all of this here. And this here, well, if you have to do it in pieces. I don't think you can watch that until the end. So it's 2x minus 1 by 2x minus 1. So what's happening here? So 2x by 2x gives you 4x squared. 2x by minus 1 gives you minus 2x. Then this one, this minus 1, sorry, by 2x gives you minus 2x. Minus 1 by minus 1 gives you positive 1. That simplifies to 4x squared minus these two becomes minus 4x plus 1, right? And that's how we got this here. When you remove this bracket now, well, this is going to be a minus. That's going to become a plus. And then this plus side is going to be a minus thing. When we simplify all of this, we will get minus 4x squared plus 10x. And you can see where the 10x comes from. This 6 and this 4. And -1 and -1 becomes -2. Right? A little complicated, right? Good. And then the other way around now, the composite of G and F is where we put the whole of Fx in G, and this is what happens. We put in 2 plus 3x minus x squared in the place of x here. Right? And that's what we do. Remove the brackets, simplify, and we get this here. Note that this here and this here is not the same. Therefore, the composite of F and G is not equal to G and F, or the composite of G and F. No, they're not the same. However, if you were to find a product, FG, right? The composite of the two, and you were to find GF, composite of that, sorry, the product of that, they are going to be equal. So the product is the same, regardless of which one is in front. But with the composite, they are different, as you can see in this example. Right. So let's take some time on the Good. Just to illustrate function composition, right? Look at this this here. So we take an input 0, 1, and we pass it into the function gx, right? So we take 0 and 1, we take it, we multiply it by 2, and then we subtract 1, and we get -1, 1. We take the output now of gx and we put it into fx, right? So the output of gx becomes the input of fx, right? And we produce another output, right? We put -1 now in the place of x, then we put 1 in the place of x, and we get this output. Now, if you were to use the composite of f and g, and you put in 0 and 1, you will get -2 and 4 directly. You see? So the composite does what 2 of these functions would have done, right? The composite of f and g accomplishes what gx and then fx would have done, right? So it is a single function that can do what 2 other functions can do. Note the order though, right? The one on the inside gx is the one that was done first. Keep that in mind. So this is a good illustration of what composite functions can do. It can do what 2 or more simpler functions would have done. Just like your cell phone. It does what your telephone, what your camera used to do. So the last thing we're going to do is what we call the inverse of a function. Now, the inverse of a function, I think this slide has a lot of things that might confuse you, right? The inverse of a function, Usually, right? You may get another function when you invert a function, but you may not sometimes, right? But forget that. That might be a little technical for you. But when you have a function and it's inverse, what happens? One function reverses the operation of the other. So if, okay, fx takes a certain input and produces a certain output, gx, which is the inverse of fx, will do the opposite. It will take that output and produce back the input. Right? That's what the inverse of a function does. Let's go to the process. This is a little complex here. Let's go to how you find the inverse. Right? And this is to illustrate what we're talking about. Fx takes -1 and 4/3 and gives you -5, 2. Gx, which is the inverse of fx, will take -5 and 2 and give you -1 and 4/3. You can try it at home and see if that's not true. Now, how do you actually go about finding the inverse, right? This is the process here. You first let y be equal to fx, very easy. Then you interchange x and y. Where you see x, you put y. Where you see y, you put x. And then you make back y the subject. When you have done so, you replace f inverse x with y, right? Or you replace y with f inverse x. And what you have done there is finding the inverse. Now, all this wording seems very difficult, but an example will really bring it up, right? So look at this. This is a simple example. Fx equals 3x minus 2, right? Find f inverse x. So what we do, we replace fx with y, right? So where we see fx equals y. So you get y equals 3x minus. Interchange x and y, and this is what you get. Now you make y the subject again. So what we do, we bring over the -2 over here. We get x plus 2 equals 3y. And then we divide throughout by 2. So when we bring the 3 over here, it's like x plus 2 over 3 or 1/3 of x plus 2. And if you multiply that in the bracket, you get this. Now this here is f inverse of x, and that's how you write it. F with a little -1 on top. Right? It's equal to that. And that's your inverse. Right? Is that simple enough? You could follow this example.
Yes, sir.
Good. This is a little application of the inverse, right? So they give you a function to find the inverse, and I think this is a difficult one. I think I should use a different one. I'll use a different one. Just keep this in mind. A function and its inverse are really mirror images of one another in a line y equals x. Right? This is a little advanced for you. But let me stop and I'll go to the whiteboard. And we're going to do a simple one like what you saw here just now. So let's say you're given a function, right? Given fx equals to 2x minus 1, right? And they say find f inverse x, right? Hence, solve the equation 2x minus 1 equal to 3. right? Good. So what's going on here? So let me start with why is it they're telling you find the inverse and then solve this equation? Now, what's happening here is that, okay, there's a certain value x that will map onto 3. That's all. So in the mapping diagram, there's x here and there's 3 there. So x maps to 3. So the original function, fx does this. Fx does this forward action. But f inverse takes 3, right, and maps it back to x. And that's why we want to find f inverse x, right? So we're going to find f inverse. So we're going to follow the process. Let y equal 2x minus 1. Then interchange, x equal interchange. Interchange x and y. And we get x equal to y. Make y the subject, right? So we'll get x plus 1 equal to y. Divide so that you get x plus 1 over 2 equal to y. Therefore, f inverse x equal to x plus 1 over 2. We'll leave it as that. So now we want to solve the equation 2x minus 1. So what we'll do, we wouldn't do this the usual way. We're going to put 3 inside the inverse and it will take us to x. So f inverse 3 will be equal to x. So f inverse 3 is equal to what? 3 plus 1 over 2, which is 2. Therefore, x equal to, and see if it's not true. 2 multiplied by 2 minus 1 gives you 3. See? Good. So I think um, I've taxed your brain a lot with functions. Right? So we'll pause there. We'll stop here. Stop the recording.